Alright, so I'm going to be talking about this paper, Noisy Channel Language Model Prompting for Few-Shot Text Classification. I really like this paper because it gets at the core of the idea of how do we choose good prompts. And the way that they go about creating good prompts or engineering them is through this channel model. So what they're doing is they're computing the conditional probability of the input given the label, and they're thus going to be required to explain every word in the input. And that means you get a better prompt, right? So they find that these channel models significantly outperform their direct counterparts, and they attribute this to their stability, being lower variance and higher worst case accuracy. So yeah, the other upside to these models is that they work well in the low data regime. So channel models are required to explain every word in the input, but because you're not like directly labeling the output, that means that you're not going to be sort of as beholden to whatever your training examples are, right? So there's some really cool results on that as well that I want to get to because I think that's the main benefit of these models. So let's talk a little bit more about like what that channel modeling actually is. So most models work off of P, Y given X. In contrast, the noisy channel model maximizes P of X given Y multiplied by PY. There's some basic like probability theory that plays into this, and let me see. They talk about some similar papers here. The basic probability of this is described here. So you can use Bayes' rule to reparameterize P of Ci. That's just like whatever your classification label is, given X as the following. So from there, they talk about how they want to be able to find some argmax C to maximize the following. Px is independent from Ci, so it's sufficient to just model Px of given Ci times PCI, and we can further figure this out based on like whatever the cardinality is of your vector of like choices for classification. So they also look into this direct plus plus method. So that is relatively straightforward. It's explored in this other paper, which sounds super interesting. Would be motivated to read that more. So they're interested in methods where there is no trainable parameters, or the number of trainable parameters is roughly smaller than 0.01% of the total. So you can imagine a zero-shot setting for this. You can imagine a concat-based demonstration of this. Concat-based is it's kind of like an analogy where you have your inputs and labels for however many K examples you want, and then you have whatever your new input is, and then you're saying, hey, predict the label from this, right? So that's what they're showing here. And then they also have this ensemble-based demonstration. I won't get into this too much, but this is just like an alternative. They obtain output probabilities from a language model, K times, condition on one training example at a time, and multiply the resulting probabilities, which they discussed there. So those are like the three ways in which they're actually going to handle the training process. The next question is, okay, well, what are we actually tuning? So there are three answers here. There is one head tuning. So they're taking the actual like heads, the hidden representation from the last transformer layer to the logic values. The transformation tuning. So they're training U, which is going to come from here. So similarly, like within like the actual model. And then we lastly have our favorite prompt tuning, and they're following Lester's method of taking like the prompt at the very input of the sentence. It should be noted that like head tuning and transformation tuning are somewhat closer to what is going on in Li and Liang, which is they have some interesting findings there. They talk about the data, talk about the experimental results. I like their pictures and data output more generally. So they're going to look at these three approaches, right? The ensemble, the concatenate-based, and zero-shot approach. And they're going to compare then, furthermore, the direct tuning, the direct plus plus tuning. That's the one where they also like balance out the like null like case in terms of predicting the output. And then their favorite and new method here, channel tuning, or I guess like channel method that they're going to use to do tuning. So let's get into it. They clearly show that their channel method works best. You see some cases in which direct++ does somewhat well, but on the whole, their method works better. The second digit here is the worst case performance, and then the first one here is average, which I like reporting, like very clear that they're not like overly cherry picking, right? If they give us that. So I think what is interesting here is we're saying that the concatenate-based versus the ensemble-based models, it's sort of split between there, but channel method is going to work the best in terms of modeling this. Then the other thing they're showing here is performance of tuning methods with a limited number of trainable parameters. So this gets more into detail on like the different types of like sections that they're using to actually train and learn parameters from. They show some cases in which that direct training is going to work better. And they're specifically looking at prompt tuning as like their preferred method for the channel method, and they show that on the whole that is going to do better than a direct training method. So further giving credence to the idea that their like model is good. Other valuable things to try: varying the size, or ablations to try varying the size of the language model. So yeah, I think this is not quite what we would expect. Like I think I would expect to see a little bit more of a like positive trend in these graphs based on what we know from these models, but yeah, I mean, it's still some positivity. The other thing they're also looking at is varying the number of training examples. I don't need to explain this. So this piece here is they're looking at model performance when there is at least one label at test time that was unseen during training. And this is supposed to really get to the idea that, okay, like we can work well with data that we haven't seen before. They do show some benefit for the direct all method, but on the whole, channel prompting is going to work better, and this almost always works better compared to the zero shot setting. Now, impact of imbalance in labels. I think that this graph here is where they're showing like, hey, this is like super useful. So they're looking at two different Ks here in terms of the like fine-tuning steps that are used, and then the P minus here is the amount of like negatively labeled data available. So what they're showing is even if we have like a super imbalanced data set, we don't actually have like crazy drop-offs in performance, which you would get with basically any other method. This is kind of crazy to me. Like I definitely want to like understand more about like the details of how this works with respect to the like conditional probability that they're generating for the like via Bayes. But yeah, I think that this is like the main value here. Like imbalanced data set. Obviously, you could do your like why am I blanking on this? You can upsample like your negative labels, but if you can't do that, this method works really well, and that's like the main value here. They also show model performance when transferred to unseen data, and this again is just really driving home the point that these models that work with like Bayes' theorem have a lot of value in terms of like generalization abilities, which I think having worked a little bit with these kinds of models in the past, like this makes sense. So some of the findings. Direct head tuning is oftentimes more competitive than previously thought, and different methods are preferred given different conditions. This direct head tuning, I think, is like the statement here is valuable because it says, hey, like Lester may be simpler and maybe the more intuitive approach, but papers similar to Lian Liang definitely have their value as well, or tuning internal parameters is valuable. So yeah, they again specify what I said. If you have just a few training examples, then that is going to be a case in which you would want to actually use this method. So the generalization unseen labels is required. They again specify that this is because the label space is indirectly modeled, and yeah, you just won't get that with your standard supervised learning setup. So yeah, the piece that I definitely want to highlight here, because I think this tells us a lot about prompting more generally. They say if the task is too different from language modeling, even with carefully chosen verbalizers, head tuning outperforms prompt tuning. It's not as easy to use channel models for non-classification tasks when modeling prior distributions is non-trivial. Or sorry, I'm getting ahead of myself. They specify that this task being close to the language modeling objective is important, and different types of tuning will affect this because it benefits from directly updating the parameters of the language model. You almost change your language model to being a classification model, right? Depending on where you're actually instituting the updates. So that's why head tuning would outperform prompt tuning, because prompt tuning we're just working with the inputs, right, and trying to keep things as close to a language modeling task as possible. So this whole sentence here, worth 1,000 words. So that is mostly it for this paper. They have some interesting discussion, but looking forward to talking more.